What are these?
Yes.
So, sleep is a state of unconsciousness, right?
Yes.
But this state is reversible by sensory stimulation. So you can call the person and actually arouse them, or you can, shake them, right? So you can touch them. But coma is a deeply unconscious state that is not reversible by sensory stimulation. So this is the difference between the sleep and coma. And between these two, we have other states of minimized consciousness, okay? But they are mainly clinical states, not physiological states, like vegetative states, okay? When we talk about consciousness in this class mainly, we mean this one, being awake. But it doesn't mean that consciousness, anybody that is awake is conscious. Okay, sometimes there are deviations between these two, consciousness and wakefulness. For example, one example is that you can think of a person which is sleep now, right? And he or she walks during the sleep, so she has sleepwalking, right? So they come out of the bed, they walk, they actually, they bypass the chair, right? So they go and open the door of the fridge, but they are not awake, right? They are not conscious. They look awake, but they are not conscious, right? So they don't know about what is happening in the environment, right? So consciousness is not always actually equal to being awake, right? But being aware of the world and self is a better definition of consciousness. But these actually are some philosophical terms, and we don't want to talk about them, okay? But today, when we talk about consciousness, we mean simply being awake, right? So the third life, the third of our lives actually is spent in this sleep. So if you are, for example, 30 years old now, maybe, okay. So this means that for 10 years you were sleeping, right? You were asleep for 10 years. So it's a substantial part of our life. And it also occurs in all mammals. So from an evolutionary perspective, it's also important, right? Sleep. And clinically, we have high prevalence of sleep disorders. So again, it's very important, right? So the reason why we are talking about the sleep during this class is evolutionary perspective, clinical prevalence, and so on, right? So the sleep need is different depending on the age. For adults, we sleep for 7 to 8 hours a day. For teenagers, we have 9 hours at least, the need for sleep, and infants will sleep for 17 hours a day. So in this figure, you can see the distribution of the sleep need in the population, right? So you can see that sleep length is here, and the percentage of people is shown here. So most people sleep about 7.5 hours a day, right? But between 6.5 to 8.5 actually accounts for most of the population, right? And here you can see the change of the sleep need with the age. So from birth to death, there is a decreasing trend in the need for sleep. So a newborn baby, sleeps for about 16 hours or 17 hours. Then at 1 year age, they sleep for about 12 hours, right? Then it decreases. So at 10 years old, they sleep for 10 hours, and this trend decreases, right? At 20 years, they sleep for 8 hours, right? And after that, this decrease continues. So you may know that, old people usually sleep for 6 or 5 hours a day, right? So as people age, they tend to sleep more lightly and for shorter times at night, right? So sleeping. And the other question is, or the other thing that we should mention is that we don't know the reason why they sleep. It looks very simple, but actually there is no scientific support for any reason we think. So, for example, we have some theories only. One of these theories says that energy conservation is the reason why we sleep. So, energy conservation theory maintains that we need to sleep to replenish brain glycogen levels. You know that brain only depends on glucose. It cannot metabolize other things like fats or proteins. Okay, so it only relies on glucose for metabolism. And for glucose metabolism, we need glycogen. During the sleep, the sources of glycogen is replenished and reversed, right? So metabolism also decreases during sleep, and it can keep the energy in the body and in the brain, right? So this is one theory. Another theory said that it's necessary for survival. If we prevent a rat or any other animal from sleeping, they die after 1 or 2 weeks. So in research, we usually use a device that has water inside and some platforms, right? The diameter of the platform is adaptable. So we usually put rats on these platforms. If they go to sleep, if they fall asleep, they fall down in the water. So they get awake and they come up again. So whenever they fall asleep, they fall, right? So they cannot sleep. So this way you can make sure that, for example, they cannot sleep for 1 week or 2 weeks, right? So usually after 1 or 2 weeks they die. So we can say that sleep is necessary also for survival. So sleep deprivation causes weight loss, failure to regulate body temperature. So sometimes the body temperature of the rat goes up, sometimes goes down. They eat more, but they cannot keep their weight, right? And the immune system also is interrupted because they show infections. So sleep can be important for survival. Another reason for having to sleep is its restorative effect. And there are some studies that show that this one is maybe more important than others. The restorative effect of sleep. For example, now we know that during the sleep, the size of the brain decreases. So you know that we have intracellular fluid, extracellular fluid, right? During the day, the brain works. You have action potential. Action potential means ions go into the cell. So the cell, and after that we have osmosis, right? Water actually follows the iron, so they go into the cell, so the cell becomes larger, so the environment of the cell becomes smaller. And the extracellular space becomes smaller during the day. Okay, this actually prevents clearing of some of the substances from the extracellular fluid, right? But at night, during the sleep, everything is reversed. Ions go out, water go out, cells become smaller, and the extracellular fluid expands, right? So now, for most of the substances, it's possible to go out of the brain. Okay? One of these substances is amyloid. Okay. You know that this, I don't know if you know this or not, it's very important for Alzheimer's disease. Okay? When it goes up, the person usually goes toward Alzheimer's disease. Okay, so the problem in Alzheimer's disease is accumulation of this protein in the brain. So, when the extracellular space expands, this protein, this peptide, can be cleared off from the brain. But when it shrinks, this remains in the brain and it can increase the probability of having Alzheimer's disease. And this was shown in some rats, for example, in some mouse. So there are some mouse with genetic manipulation that show Alzheimer's disease after some years or after some months. So we interrupted some genes in the brain of this mouse, and it's very probable to have Alzheimer's disease after several months. Okay? So if you deprive this animal from sleeping, usually Alzheimer's happens sooner. So this shows that this theory maybe is more important than other theories. Okay? So another reason for sleep is memory consolidation. Consolidation means conversion of short-term memory into long-term memory. Right? This usually happens during the sleep. So sleep is important for that. In humans, lack of sleep causes impaired memory, reduced cognitive abilities, mood swings, and sometimes hallucinations. Some patients with fatal familial insomnia have problem going into deep stages of sleep. So they cannot enter a state of deep sleep. And usually they die sooner. So some scientists believe that this earlier death is the result of this problem. Okay? So we can compare this one with this one. Okay? Sleep deprivation in rat causes actually death, right? So the same may happen in humans. So if there is any problem with the sleep, usually the person dies sooner. Okay? So these are some reasons for having this. Okay? But we are not sure about any of them. These are only some theories. Okay. So now let me talk about the ways we can measure the sleep. Okay, the quality of the sleep and make the sleep quantitative, right? So we have several measures for this sleep. But three of them include EEG. What is EEG? What does it stand for? Electroencephalography. Electroencephalography, which records brain waves. We have EOG. What is it? electro-oculography, and EMG.
Electromuscular.
Not muscular. Electro. So you should use the Latin word, no?
Myography.
Myography. So electroencephalography for brain waves. Electro-oculography for eye movements. Electromyography for muscle contraction. Right? Tone of the muscle. So usually we use these three measures or three tools to describe the sleep quantitative. So let's see EEG, electroencephalography. So for recording EEG, you should put several electrodes on the head, right, on the scalp. So the number of these electrodes and the location of these electrodes actually follows a universal principle, right? So the locations are standard, the number are standard, right? So we put electrodes in the frontal lobe, on the frontal lobe, parietal lobe, occipital lobe, temporal lobe. There are some reference electrodes usually, and they are connected by way of some wires to a device called amplifier. So it amplifies the signals, right? And it also filters some unwanted signals. So the only thing that remains is the brain waves, waves that are coming from the brain, right? So the recording looks like this one, okay? So you can see that we have some actually irregular waves that don't have any pattern, any specific pattern, right? So we call this EEG. But we divide them based on their frequency. So let's compare this one with a wave recorded from the heart, right? T wave, Q, R, S, and T wave, right? P, Q, R, S, T. We know that this one originates from auricles, right? This one comes from ventricle. It's actually a contraction of the ventricle. And this one shows relaxation of the ventricle, right? And this pattern is fixed and is repeated several times and continuously, right? But this, I mean, in the EEG, we don't have any specific pattern. Only some irregular waves, right? So in order to classify the waves, we need to rely on the frequency, not on the pattern. So the frequency of these waves is shown here. The slowest one is this one, delta wave, which has a frequency less than 3.5 hertz or cycle per second. After that, we have theta waves, which has a frequency between 4 and 7. Then we have alpha wave, which has a frequency between 8 and 13. And then we have beta wave, which has a frequency between 14 and 30. Right? So you should know the order of these waves and the frequency. So less than 4 is called delta. 4 to 7 beta, 8 to 13 alpha, 14 to 30 beta. We have also another wave called gamma, right? Which has a frequency more than 30. Gamma waves. Right? So, alpha wave is recorded from the parietal and occipital lobe in a person which is awake, but the eyes are open. So You are now actually awake and the eyes are open. Right? Sorry, eyes are closed. Yes, closed. If we record from the parietal cortex and occipital cortex, we can record alpha waves. Right? So occipital lobe, parietal lobe, the person is awake and relaxed, eyes are closed. Beta waves, this fastest one, right, is recorded mainly from parietal and frontal region in an alert person with the eyes open. Right? Beta waves, this one, is recorded from the parietal and temporal regions, usually children. So you cannot record this wave during wakefulness in an adult. Right? But also delta waves, which is the slowest one, is recorded during deep sleep and also in infancy. Right? So you cannot record delta and theta waves from an adult brain during the wakefulness. But in the sleep, it's usual and it's normal to record these.
Doctor, so do we mean like when we are awake, we can, for example, the sound that we hear while we closing our eyes is different from the the cortex or the lobe cortex is different between the
sound or wave, you mean?
The wave.
Yeah, the wave is different, yes. So, you are awake. If your eyes are open, you can record one type of these waves, beta. If you close your eyes, it is changed, it is converted to alpha wave.
Is that going to affect on the wave itself and store it in, for example, for a long time or for short time or no?
Short time? What do you mean? You mean, actually, I didn't get your question. Okay, you mean, does it affect our brain activity? You mean?
Yeah.
Yeah, it doesn't affect the activity of our brain. It is a result of our brain activity. Okay? So, when your brain is active, very active, the result is changing these waves into higher frequency.
So why was it
When-
different?
Why they are different? So, I will talk about this. Okay? So, you should memorize the frequencies, the location we can record these waves, and the condition we can record that, right? So, part of your question, okay? So, alpha waves are recorded when eyes are closed. You can ask the person to open their eyes. By opening the eyes, frequency increases, amplitude decreases, right? Alpha is converted into beta. Again, eyes are closed, so beta is converted to alpha, right? So we call this conversion desynchronization. Let's see here why we have EEG waves to answer your question also. So, you know that in the brain we have cortex and subcortical areas, right? We put electrodes on the skull. Which one is closer to skull? Cortex, right? So usually we say that EEG is recorded from cortex, not from subcortical area. So EEG is a representation of activity in the cortex. And you also know that cortex has 6 different layers, right? The most superficial one is layer 1, the deepest one is layer 6. In layer 5, we have pyramidal neurons that are large. And they send the dendrites to layer 1. And they send the axon to subcortical structures, right? And they are very close together. So we can think of a plane of pyramidal cells in layer 5. Right? Dendrites goes up, axon goes down. So it's like this. Okay? So the dendrite is positioned vertically. So we have basal dendrite, apical dendrite. Basal and apical. The other thing is that cortex receives different type of inputs. Some of these inputs come from thalamus, so we have thalamocortical inputs. Some others come from other areas of cortex. We have corticocortical inputs. So, thalamocortical inputs, corticocortical inputs. Okay? Thalamocortical inputs enter layer, what layer? Inputs from thalamus come to layer 4 of the cortex, right? So layer 1, 2, so we have pyramidal cells here, right? Action goes down, dendrite goes up. We have basilar dendrite also here. So corticocortical input come to layer 1 and 2. So from cortex. Other regions of cortex, right? From thalamus, we have input to layer 4. So layer 4, layer 1, and also layer 2. Okay, some of them go to layer 2. So, let's consider that these neurons release glutamate, an excitatory neurotransmitter, right? So glutamate is released here. Glutamate is excitatory, it binds to receptors, opens cation channels, ions go into the cell, so positive charges go in, right? What happens to extracellular part of the cell? So when sodium goes in, outside of the cell become negative. Okay? So imagine that here you have inside of the cell and inside of the dendrite, right? So positive charges are here inside the cell. And you know that inside of the cell in other layers is negative. We have resting membrane potential which is negative, minus 17 millivolts, right? So this positive charge tends to go this way, right? So when this one is minus, I mean this region is minus, positive charges that are here tend to go this way. So from positive side to negative, from positive to negative. So we can say that we have a current like this. Right? That goes actually along the dendrite. So here is negative, here becomes positive. Where is the electrode? Here. So we have electrode here, which is close to this negativity. Right? So when corticocortical inputs are activated, they release glutamate, and we have synaptic activity. EPSP is generated here. So this positivity means EPSP, right? So EPSP is generated here. So this electrode record a negative bit like this. Now, let's see this one, thalamocortical. When thalamus is active, synaptic activity happens here. So ions go into the cell. So this part becomes negative. Right? So ions go into the cell, so they become inside the cell is positive. So this positivity go that way. Here we have negativity, right? So negativity and this comes here. So we have another current this way. Right? So here we will have positivity, here negativity. This electrode will record a positive wave. Do you agree?
Mm-hmm.
Don't agree?
This again?
Again?
Mm-hmm.
Yeah. So, when you have cortical activity, we come here, release glutamate. Glutamate opens sodium channels. Sodium goes into the cell, right? So inside the cell we'll have positivity. Outside we'll have negativity. Why? Because all ions went into the cell, right? So we have negativity outside,
Yeah.
right? The positive charges inside the dendrite go this way because we have positivity here and the rest of the cell is negative. So positive charges tend to go towards negative charges, right? From here we have outside negativity. The rest of the cell is positive outside. So these positive charges tend to go this way. So we have a dipole out of the cell. Superficial layers are negative, tip layers are positive.
Positive.
The electrode records this negativity. Why? Because this one is closer to the electrode. Right? This one is closer.
Right.
So it records a negative wave.
Yeah.
Right?
Yeah.
So now, ignore this one. See this one, okay? We have thalamocortical impulse. From thalamus into layer 4, deep layer, not superficial. So synaptic activity happens here. Glutamate is released here. Sodium goes into the cell. Inside the cell becomes positive. Outside becomes negative. So outside the cell will have negative. So now these positive charges go that way, upward. Right? Positive charges that are here in the rest of the dendrite, they tend to come
To the negative side.
yeah. So here is negative, here is
Positive.
positive. So the electrode can record this positive.
Yeah.
So it shows a positive wave.
Mm-hmm.
Right? So based on this, we can conclude that EEG is the result of EPSPs and also IPSPs. I didn't talk about IPSPs, right? So it's the result of synaptic activity, not action potential, not other type of potentials. Okay? Synaptic activity in the brain causes causes these waves, right? So, in this, for example, here in this part, when we have positive wave, it means it was made by an activity from thalamus. When we have a negative wave,
Cortical.
it means it is made by a cortical activity. Right? So, now, I told you that cortical would come here and release glutamate. If we release GABA, everything is reversed. Right? Instead of having negative wave, we'll have positive wave. If it releases, yeah. If this one releases GABA, this positivity will be
negative.
So, a positive wave is a result of IPSP generated by cortical inputs or EPSP from thalamocortical impulse, right?
Right.
A negative wave can happen as a result of EPSP, corticocortical impulse, and IPSP in actually, yeah, negative one. IPSP in thalamocortical input. So again, we cannot rely on the pattern of these waves.
Yeah, because maybe there is a gap.
Yeah. So physiologically, it may happen in an irregular manner, right? But we should rely on the frequency of the waves. So how frequency is determined?
So I have a question.
Yeah.
Could you please back to the that slide?
This one?
Yeah, that's one. What about that way while eyes is closed?
You mean this one?
Yeah, just.
So when we
is
open
it
the
the
eyes.
same? Yeah.
Yeah, I will talk about this. Okay? So far I've talked about the reason we have positive waves, negative.
And negative.
Okay? So now I'm going to talk about the frequency.
I think that it's same, but the frequency is different.
Yeah, frequency is different.
Yeah, but the name the same.
Not the same mechanism.
Ah,
It's,
okay.
we have another mechanism for frequency.
Okay.
Okay? So before I talk about frequency, again, you can see this figure. Corticocortical impulse activate the cells here. Outside the cell becomes negative. Positive charges from here tend to come this way, so we have blood flow, right? Positive in the deep layers, negativity in superficial layers. So the electrodes will record negative wave, right? Okay. Now, let me talk about the frequency. Okay, it's better to talk here, right? So the same pyramidal layer, we have 6 neurons here, right? So they receive thalamocortical impulse, corticocortical impulse, right? So, and we have recording of synaptic activity here and here from these neurons. Neuron 1 is recorded here and here. So, first, let's imagine that all of the incoming inputs to the cortex are activated at the same time. And the activity is synchronized. Right? So, let's see synchronized state. So, these fibers come to the cortex, they bring action potential. Action potential come here all at the same time. Right? So we'll have release of neurotransmitter on these neurons at the same time. So postsynaptic activity happens again at the same time. So EPSP neuron 1, 2, 3, 4, 5, 6 happens at the same time, right? So we have EPSPs in these neurons at the same time. The next action potential comes. Second one. Again, we'll have the second EPSP in all of these neurons at the same time, right? The third one comes. The result will be third EPSPs and so on, right? So the electrode which is located on the scalp records the sum of activities in all of these neurons. So the sum of these EPSP is a wave like this. And the sum of these activities is another wave. Some of this is another wave. Right? So EEG is the sum of all synaptic activities in neurons under the electrode. Right? So keep in your mind, let's focus on this. In this example, or in this state, imagine that neurons bring action potentials at different times. Right? So, action potential comes, for example, sooner in neuron 1, after that it comes in neuron 3, and then in neuron 5, okay? So, we'll have EPSPs at different times. in these modes. And the electrode on the skull records some of these activities. Okay, so here at this moment, you can see that we have a positive wave, nothing here, nothing here, nothing here, nothing here, another positive wave. So we have two small waves here. So the sum of these activities is a small wave. Right? But the next moment, you have a very large negative wave here, nothing here, a small negative, a small positive, another negative, nothing here. So the sum is negative. So we can go forward moment by moment, right? You'll see that the waves are different now, right? There are some of these activities in neurons. So if you compare this one with this one, you can find out that here we have low frequency waves with higher amplitude. Here we have higher frequency waves with lower amplitude. It's similar to beta wave, but this one is similar to delta wave. Right? So what is the difference here? I mean, what causes this difference? Synchronized activity or irregular activity. If neurons in the brain are active and their activity is synchronized, we'll see a low frequency wave with high amplitude, high voltage. Right? If the neurons are active irregularly, then the result will be a high frequency wave with low amplitude. Right? So let's go back to this slide, this one. Eyes are closed. We have alpha waves. Frequency is lower, amplitude is higher. Why? Eyes are closed, right? There is nothing from the eyes to the occipital lobe. So neurons don't receive any excitation from thalamus. All excitation is low. So they tend to become synchronized. The synchronized activity generates a high amplitude, low frequency wave.
So is that effect because of the thalamus activity is closed?
Yeah. So thalamus dictates this type of wave to the cortex.
Oh God.
Okay?
Yeah.
So, the other thing, when eyes are open, then we have input from eyes to the thalamus, from thalamus to the cortex. So neurons are activated, but this activity is desynchronized and irregular. So the wave becomes low amplitude, high frequency. Right? So now, you know the basis, the physiological basis of having different polarities of waves. Why sometimes we have positive waves, why sometimes we have negative waves. And you know also the neural basis for having different frequencies. High frequency or low frequency. Low frequencies result of a synchronized activity of neurons, but high frequency is a result of irregular and desynchronized activity of neurons in the brain. Right? So you can use EEG for measurement of sleep, but also for measuring for evaluation of some diseases.
Like
Right. Like what?
Like I don't know. I think that Alzheimer or something.
Maybe Alzheimer, but the most important one is epilepsy.
Yeah.
Seizure and epilepsy. Right? So let's say the EEG. So, first of all, you should know that when we record EEG, we should compare the potential of one electrode with the potential of another electrode. So we have several electrodes on the brain. So imagine that one is here, another one is here. Right? So each of them are recording the potential. So we, for example, subtract potential from this electrode from this one. So the result will be shown like this. Okay, so electrode number 6, electrode number 7. So this one is 6, this one is 7. The difference is shown there, right? 10 to 11. The electrode is here. 10, 11. The difference is shown here. So you know that voltage is a difference of potential, right? Between two locations, 2 points. So we have several channels. We call them channels. The difference between two electrodes is called a channel of recording, right? So in this person, EEG was recorded. You can see that most of the time you have alpha waves because the eyes are closed and the person is awake, right? But for some seconds, you can see that we have high voltage waves that are low frequency.
Does he open his eyes?
No, the eyes are closed. Okay. And this happened only in 2 of these channels, not all. And it happened only for 2 seconds or 3 seconds. Right?
Okay.
What does it mean? So we have normal brain activity here. All of a sudden, we can see an abnormal activity. I told you, beta waves or delta wave shouldn't be recorded during the wakefulness from an adult brain. Okay? Now you can see delta waves. So this means neurons are synchronized in this moment. Right? Synchronization here is not normal. Synchronization here is abnormal. So this shows a seizure activity only for 2 seconds. Where in the brain? So this channel, the difference between these two, and this one, the difference between these two. Which one is common between these? This one, right? So where is the location of this seizure activity? Temporal lobe on the right side. Right? So, on the basis of EEG, we can identify some disease states.
The two PDBs was here?
Here.
Yeah.
So, the normal activity of the brain during wakefulness should be alpha or beta.
Yeah.
Right? So, in this patient, in the temporal region, on the right side, for 2 seconds, we have delta waves. It's not normal.
Yeah.
It shows some disease states. Okay, we should know that one of the diseases that may cause delta waves during wakefulness is seizure. You know seizure?
Seizure?
Yeah, seizure. So epilepsy. So you call in Arabic sad.
Oh, epilepsy.
Okay?
Yeah.
So seizure. Right? So in seizure we have synchronized activity of neurons, and these activities uncontrolled. Right? So they may cause some signs in the body like contraction of the muscles that are unwanted and uncontrolled, right? So this shows the seizure activity in the brain. Another one is here. Let's see this one. So normal activity of the brain, right? And then suddenly it is changed to this type of activity. What can we see? Large waves and low frequency. It's delta wave again, right? But we have a specific pattern here. The pattern is like this. We have a wave and a line called spike. You know spike? So let's see this one. We have wave and a spike. Wave and a spike, right? So it's like this. Okay? So wave and spike. Sometimes it's called doom and spike. right? So this pattern continues for some seconds, usually up to 14 seconds. And this happens in all channels. So it means all areas of the brain are involved. Temporal region, frontal region, occipital region, parietal region, everywhere. Right? So this is another sign of seizure activity, but the type of the seizure here is different. We call this absence seizure. Absence seizure. During this attack, the patient is not conscious, but the posture and position remains normal. So you're talking to the person, the patient, he or she experiences a seizure attack like this, absence. Okay? Position is maintained. So he or she was looking at you and it continued to look at you, okay? So you cannot identify anything. But during that time, the person is not conscious. Okay? So he or she is unconscious, but she's not aware of that. Okay? After 14 seconds, they come again. Okay? So they are conscious again. So we have a type of seizure that consciousness is lost, but posture doesn't lost. Is not lost. Right? So we call this absence because the person is not present here, mentally. Right? So that's why we call this absence seizure. So this is a type of generalized seizure. So all areas of the brain are involved. But the other seizure I mentioned before in this slide was a focal seizure. So focal seizure, generalized seizure. So all I wanted to say is that we can use EEG to identify some diseases. One of the most important diseases that can be identified by EEG is seizure, because it shows synchronized activity of neurons. Right? So we can also use EEG to measure the sleep and wakefulness. Let's have a break. After 10 minutes, we will continue.